Okay. We will look now to the exact definition of DC and AC. And it's very important to clarify it now before we start to power electronics, because it's sometimes we need to convert from AC wave to DC, and sometimes from DC to AC, and sometimes from AC to AC with different frequencies, or from DC to another DC level. So we need to distinguish between them, and we need to understand what's happened to wave to become from from AC to DC, or from DC to AC. So let's have a clear definition what's DC and what's AC waveform. Okay, let's start with the DC. DC, we need to understand the source of DC power. Usually it's come from battery or from solar cell or from AC wave converted or rectified to DC. Okay, so if we take as an example the DC source, and you connected it with the resistor R, and that's the current I, and that's the voltage. Now, if we plot the relation between voltage and current, so that's our scale. So that's usually time with the second, and here it's the amplitude. Now, if our waveform it's a voltage, so that's the amplitude of voltage of the battery. For example, 12 volt. So that's it will be our 12 volt. Okay. Now let's look to the current. The current based on Ohm law, I is equal V divided by R. So the current also it will be similar to the voltage. It has a fixed magnitude or amplitude and one direction. So now the current here, it will be V divided by R. For example, if R is 2 ohm, the current it will be 6 ampere. So that's it. Now it's 6 ampere. So the distance from here to here, it's 6 ampere. Okay. So now if we look to the load here, we will find it's a resistor. So that's always the behavior of the current if our load is a resistor. Now if we add an inductor or a capacitor to the load here, okay, by the end, the shape of the current or the voltage, it will not change. It will has a transient response. Then it will remain with a constant value. Okay. Now, if I have, that's we call it linear load. If I have a resistor or capacitor or inductor, that's we call it linear load. If I have something it's non-linear load, is the behavior it's remain the same or not? That's what we will do it in the future. Okay. So that's now the behavior of DC circuit. Now, if we substitute that with the AC, if we substitute power source with the AC source, let's see the difference between them. The current, it will be small I, resistor, it's the same, and the voltage also, it will be small v. But the way we write the voltage, it's become V of t, it's equal sine omega t. For example, here it's 2 pi f T. So that's my voltage. And if the frequency is 50 hertz, now and don't forget the maximum value here of the voltage. For example, if we take 12 volt, so that's V of T. So now that's it's 12 sine. If the frequency 50 hertz, that's it's become 100 pi times time. Okay. Now let's plot that behavior here and let's see the difference between voltage and current. So the voltage, it will take a sine wave form. It has a maximum value 12 with the frequency 50 hertz. Now let's look here. We will see we have a maximum value V max, which equal 12 volt, and also we have another V max in opposite direction, which equal minus 12 volt, and we have another V here, we call it V peak to peak, V peak to peak, which equal 42 volt. So from the voltage from peak to peak, it's called 42 volt. Okay, so now we can see the voltage, it has a sine form, and this sine form, it has a maximum value, as we can see here, it's 12, and this sine wave, it's repeat itself at a certain time, which we call it period. So now if we say this wave, it has a 50 hertz, that means this signal, it's repeat itself 50 times in 1 second. So if we take a scale of 1 second, we can say this wave, it's repeat itself 50 times. So if we take that as 1 second, so we can say the frequency, it's equal 50 hertz. That means this signal, it's repeat itself 50 times in 1 second. But now if we take just one cycle, and we look to that time, and this time we call it period, and give it symbol T. And the period, usually it's equal 1 over frequency, and the frequency, it's equal 1 over period. So that's the relation between them. So now, so that's our period. You need to distinguish between the period and the time here. They are not the same. That's also another common mistake students they do it. This is T, it's time. It could be 1 second, 2 seconds, 100 seconds, whatever. Because once you time by omega, you will get angular. You will get your angle. You will get your angle. Okay. So now, if we look to the maximum value, we find that it's move from 0 to a certain value, up, maximum, then it's back down, 0 again, in a negative direction, then to the positive direction again. So now we can see this signal at a certain period, it has a positive values, and another period it has a negative values. So what's that mean? It has two direction. So in our circuit now here, at the first cycle, the current, it will take that direction, and at the second cycle, the current it will take that direction. And that is very important when we look to the semiconductor, to the power electronics, how does it work? The direction of the current is very important, and when we start design inverters or rectifiers or so on, we will see how that is very important. Okay. Now the question is, when we compare AC signal to DC, usually we will not get it a pure DC signal. Usually we will not get it a pure DC signal. The requirement, we need pure DC signal. But if I compare that to DC, usually we will not get it a pure DC. Usually we will get it nearly DC signal, but it's not DC signal. It could be, we get it like that. So now if we zoom that, for example, we will see it. Okay. Now if we take the average of that, we will get DC. If we take the average of this point and the average of this point, our average, it will represent DC. That's why we calculate average. Okay. And the stuff above the average and below average, something we call it ripple factor. That's something we will study it before, and we need to optimize that ripple factor. And sometimes this zigzag, sometimes it's not a pure sine wave. Sometimes we will find it has similar like triangle. When we take average, that's our DC. So sometimes we have that shape, sometimes we have that another shape. So we will study something we call it form factor, which showing us how our DC close to DC from that factor, and something we will do it in future, and we will study another factors again. And that it has something we call it frequencies inside it, and we will do another thing we call it Fourier transformer to study how many frequencies inside this signal in order to design our filter to make it pure DC, to make it pure DC signal. So in conclusion, DC signal, it's very straight, very constant. It has one direction. AC signal, its direction, it's a change at a certain period. Has a maximum value, and another calculation we will do it in future. We need to calculate average. For example, average for this signal, it will be 0. We will do something we call it RMS calculation, and we will know in future what's mean RMS and how is it useful and where we can apply it. So that's something we will do it in the future. So just now you need to know your wave signal. Okay, now the wave signal, it's not necessary to be a sine wave. It could be a square wave like that, for example. That's another wave. Or it could be like that. So that's another wave. It still has the same characteristic. It still has a frequency. It still has a period. It still has maximum, minimum values, all these characteristics. Okay, so that's something we need to study it in future. If you look to the square signal, you will find it's mixed between DC value, but also it has two directions. So it's become AC. It's become AC. Usually when we say AC, people, they think only it's sine wave. Okay? We need to concentrate on this behavior. We will see this behavior in motors. When people, they studied machine before, they saw this behavior before. they simulate the current inside the machines, sometimes they see the current it's behave as a square, and that's something we studied before. Okay.